SwayamPrabha. Digital India. Educated India.
In the previous lecture, we have seen the LMTD method, and now, as you will recall, there are two types of problems, the sizing problem and the rating problem in heat exchanger. So we will now tackle the second type of problem with the Effectiveness-NTU method. We are on slide number 71, moving on to slide 72, section 5. So the first problem we have already seen, when all the four temperatures of the hot and cold fluids are known, the inlet temperatures and the outlet temperatures respectively. And we have solved that problem of sizing in heat exchanger. We found out the the area, the transfer area, through the LMTD method. And now we are tackling the second problem, which is encountered in heat exchanger analysis, which is the determination of the heat transfer rate and the outlet temperatures of the hot and cold fluids for prescribed mass flow rates and inlet temperatures. So we know the mass flow rate at the inlet of both the fluids, the hot and the cold fluid, and we also know the inlet temperatures. And the type and size of the heat exchangers are also specified. So we have chosen a type of heat exchanger, and we would like to now find out the heat transfer rate and the outlet temperatures of the fluids what are expected from this device. So in such situations, we will use the NTU effectiveness method. So we will first discuss what is effectiveness, and then we will talk about the number of transfer units, which is the NTU. Mind you, LMTD can also be used under such type of situations. However, since the four temperatures are not known, it will be iterative solutions and it will become tedious. And therefore, this method has been developed, the NTU effectiveness method, when without knowing the outlet temperatures, we are now trying to find them out through this method. So this NTU, as I said, is number of transfer units. It's a non-dimensional parameter, and we will quickly, in this lecture, we will see the importance and the definition of NTU. So first, let us concentrate on the effectiveness. What is the effectiveness of an heat exchanger? Now, this is a heat exchanger. You want to transfer the heat from the hot fluid to the cold fluid, or vice versa. Whatever you want to do here is an objective function. And we would like to find out the effectiveness of such a system. The mass flow rates are given to you, the inlet temperatures are known, and you would like to find out the effectiveness of such a system for a given device. So naturally, we need a numerator and a denominator, proper definition. So we define effectiveness as the actual heat transfer rate which is happening from this device, and divided by what is the maximum possible heat transfer rate. So we need a datum to compare so that we can define the effectiveness, how effective our heat exchanger is, and for that we need a maximum possible heat transfer rate. So let us first look at the actual heat transfer rate. So actual heat transfer rate of a heat exchanger, it can be determined from energy balance, as we have seen in the last lecture. So you have Q dot is equal to Cc, which is the heat capacity of the system, multiplied by the delta T of the cold fluid, which should be equal to, under steady state, the Ch multiplied by the delta T of the hot fluid. So this is a simple energy balance under the assumptions which we have already discussed, where the Cc and the Ch are the respective heat rates, capacities of the two fluids, hot and cold fluids, so which is basically the thermal inertia, mass into specific heat. So this is the numerator part. So numerator is simple. Now what about the denominator, which is the maximum possible heat transfer rate? Now let us look at this in slide number 74. So moving on, now let us try to understand. The heat transfer in a heat exchanger will reach its maximum value. When will it reach its maximum value? When either the cold fluid is heated to the inlet temperature of the fluid, Either this can happen because then there is no effective delta T remaining, or the hot fluid is cooled to the inlet temperature of the fluid, because inlet temperature of the cold fluid is the lowest temperature and the inlet temperature of the hot fluid is the highest temperature in the system. So whenever temperature equalization will happen, then there is no more possibility of any further heat transfer, and that should give you the maximum heat transfer rate, because whichever fluid reaches the temperature of the other fluid earlier, you will be limited by that particular fluid. So therefore, these two limiting conditions will not be reached simultaneously, of course, in general, unless the heat capacity rates of both the fluids are exactly identical. So unless Cc is equal to Ch, you will see that one of the fluid, the cold fluid, can become hot quicker, or the hot fluid can become cold quicker, depending on their respective heat capacities or thermal inertia of the system. So when Cc is not equal to Ch, which is the general case, which is usually the case, the fluid with the smaller heat capacity rate will experience a larger delta T. So this is quite sure, because Q being constant, Q is equal to Cc into delta T. So depending on whether the C is for the cold fluid or the hot fluid, so whichever heat capacity is smaller, for the same amount of heat, that particular fluid will gain maximum delta T, or it will experience a larger delta T, and thus it will be the first to experience the maximum temperature, at which point the heat transfer will come to a halt. So if cold fluid becomes hot quicker, then you are actually limited by the thermal capacity of the cold fluid, because you still have the possibility of a heat exchange is now stopped, because the cold fluid has become equal to the hot fluid temperature. Alternately, if the hot fluid temperature becomes cold quickly and it has come to the temperature of the cold fluid, then there is absolutely no possibility further that anything else will happen. The heat transfer will stop. So therefore, you have to see the smaller of the two heat capacities. So let us look at that. So to determine the maximum possible heat transfer rate in a heat exchanger, we actually note that the maximum temperature difference in a heat exchanger is the difference between the inlet temperature and of the hot and the cold fluid. So you see, this is the delta T max, which is, there is nothing which is the potential, the maximum potential difference is in the hot fluid inlet and the cold fluid inlet. These are the two maximum possible temperature difference, and therefore what we will do, the maximum potential difference multiplied by the heat capacity, which is minimum, the minimum of the two, will give you the maximum heat transfer rate. So please note, this is interesting. Just to you just have to spend one moment to understand this. The maximum potential difference, you cannot exceed this, and out of the two thermal capacities, the system is limited by the smaller number, which is the C min out of the two. So the C min can be Ch or Cc depending on the two, because if Cc is smaller, then once this much amount of heat Qmax has been transferred, the cold temperature will now become equal to the hot temperature and no more heat transfer takes place. If Ch is smaller, then after you transfer Q dot max, which is C min into Th in minus Tc in, you will see that the hot temperature has now come to a temperature of the cold fluid, and therefore no more further heat transfer takes place. So here is a small example on the right. So in this case, for example, 40 kg per second of hot fluid is going inside a heat exchanger. This is a pipe in pipe heat exchanger, which is counterflow in nature. The mass flow rate is given, the thermal, the specific heat is also specified here, and it enters at 130 degrees. You have some cold water available from the ambient at 20 degrees centigrade at 25 kg per second, and it is water, so its specific heat is 4.18, and this is hot oil. So you want to cool the hot oil with the ambient water. So what will you do? You will first find out the Cc, that is the heat capacity, the thermal inertia, which is mass into specific heat. So for the cold fluid, it comes out to be 104.5 kilowatt per degree centigrade, and for the hot fluid, it comes out to be 92 kilowatt per degree centigrade. So which is the smaller of the two? which is the smaller of the two corresponds to the hot fluid, which is 92 kilowatt per degree centigrade. And what is the maximum delta T? What is the maximum potential difference in the system? Which is TH in minus TC in. So which is 130 minus 20, which is 110 degrees. So therefore the maximum heat transfer rate Q dot max of such a heat exchanger will be 10,120 kilowatt. You cannot under any circumstance, irrespective of how large the heat transfer area you choose, even if you choose infinitely long bigger heat exchanger, you will not be able to transfer more heat than 10,120 kilowatt. And therefore now for the effectiveness definition, we move on to slide 76. The definition of effectiveness is the actual heat transfer rate is effectiveness multiplied by the maximum possible heat transfer rate, which is equal to Cmin into Th in minus Tc in, and therefore you will see that this you get a definition of what is the actual heat transfer rate from such a system. Now naturally, if Cc is equal to Cmin, then you will put the relevant let's say quantity. The Cmin has to be put corresponding to Cc, and therefore your effectiveness will become Cc into delta T cold divided by that Q max, Q dot max, which is Cc multiplied by Th in minus Tc in. So you get a non-dimensional quantity, which is the ratio of the temperature differences of the cold fluid, which happens because you are limited by the cold fluid temperature difference, and what is the maximum possible delta T in the system. Alternately, if Ch is the minimum of the two, so you will be limited by the fact that the hot fluid is going to attain the temperature of the cold fluid very quickly or earlier than the cold fluid as compared to the cold fluid, and therefore now you will put instead of the Q dot will now become equal to Ch into the delta T of the hot fluid divided by again QH max, which in this case is Ch multiplied by Th in minus Tc in, because that is the limiting condition, and therefore you will get another definition. So you have to use the effectiveness either this one or this one depending on which capacity is the lower one, and accordingly you will get the effectiveness of this particular heat exchanger. So what does this do? The effectiveness of a heat exchanger, it essentially enables us to determine the heat transfer rate without knowing the outlet temperatures of the fluid. So you have seen now in the definition that you did not know actually the outlet temperature, but since you knew the maximum temperature, the Q dot max can be determined, and the maximum potential difference, which is the hot temperature inlet and the cold temperature inlet, which are known to you, they are also available to you. So you can actually find out the effectiveness of a heat exchanger without knowing the outlet temperatures. The effectiveness of a heat temperature depends on the geometry of the heat exchange as well as the flow arrangement. So naturally, how long or how big is the heat exchanger will tell you how much is the actual heat transfer rate which is happening. And of course it also depends on the flow arrangement, because depending on how is the flow, how many turns, how many passes, whether it is counter flow or cross flow or mixed or unmixed and things like that, you will have the actual heat transfer rate. And the maximum, of course, is irrespective of this. It is limited by the minimum of the heat capacity. Different types of heat exchangers therefore will have different effectiveness relationships. So we have to now find out the way by which we can determine this effectiveness and for different types of heat exchangers. So in the next lecture, I will close this lecture because it is already about 14 minutes past. What we will do is, in the next lecture, we will illustrate the development of effectiveness relationship for a double pipe parallel flow heat exchanger. And for other type of heat exchangers, we will provide either a pre-derived analytical relationship, which will be available to you in a design data book, or the same relationship can also be represented in a graphical format. So we will see how the effectiveness can be estimated or calculated for different types of heat exchangers. For illustration purposes, we will take up only one type, which is the double pipe parallel flow heat exchanger, and then for other type of heat exchangers, we will just pick up either the analytical expression from a data book or the graphical solution which is available in your textbook. So I finished this lecture by saying that we have introduced the concept of effectiveness of a heat exchanger, which is the ratio of the actual heat transfer to the maximum possible heat transfer which can possibly take place in a heat exchanger. We have noted that this maximum heat transfer in a heat exchanger is limited by the minimum of the heat capacity values between the hot and the cold fluid respectively. And with this background, we will now derive the relationship, and we will now see how the number of transfer units, what is this NTU in the next lecture, and how is it related to the effectiveness. We will take up a parallel flow heat exchanger as an example and then extrapolate our ideas to other type of heat exchangers. So with this, we close this lecture 5 at slide number 78. So in the last lecture, we have seen the definition of effectiveness, which is the actual heat transfer rate divided by the maximum which is possible in a given heat exchanger. And now we would like to define what is NTU and get a relationship between effectiveness and NTU for different types of heat exchangers. So this is section 5 continuing at slide number 79. This is lecture 5A. So let us start with the, you will recall this logarithmic variation of the temperature differences, the ratio of the temperature differences, which we had derived when we were talking about the LMTD by the energy equation, by the application of the energy equation. And from here only we defined the LMTD. So in the earlier lectures. So if you now if you couple this with the energy equation, which is Q dot is Cc into delta T of the cold fluid, or which is equal to Ch into delta T of the hot fluid, you can make the Th out as the subject of the formula by equating these two energy quantities at steady state. And therefore your Th out will be equal to Th in minus the ratio of the thermal capacities of the cold and the hot fluid multiplied by the temperature difference which happens in the colder side. So now we can substitute this Th out in our the logarithmic equation here, and we will just add for simplicity and making it a bit more lucid. We will add Tc in and subtract Tc in, so this doesn't change the numerator. So you see the Th out is substituted here in terms of Th in and this quantity here, and you simplify. So what do we say? That we will see that logarithm ln of natural logarithm of 1 minus this quantity in the parenthesis 1 plus Cc upon Ch multiplied by the ratio of the temperature differences is equal to minus Ua upon Cc 1 plus Cc upon Ch. So this is a simplification of the original equation which we had derived when we were doing the LMTD, but since the Th out is not known in this case, we have substituted the Th out which was incidentally known when we were doing the LMTD. So we could find out the LMTD from here, but in this case we do not know it, so we have to substitute it in terms of the known quantities. So moving on to slide number 81 and simplifying this expression, we can immediately see that if you substitute this into the Q dot divided by Q dot max, which is the definition of the effectiveness, then immediately we will see that we can get a expression for, we can precipitate the expression for the effectiveness. And you should also appreciate the fact that since effectiveness is a non-dimensional quantity, so everything on the right hand side of this equation is indeed non-dimensional. So you have two non-dimensional quantities which you can clearly see here. One is Ua upon C min, and the another quantity is Cmin upon Cmax. So please mind that Cmin is the smaller heat transfer capacity ratio and Cmax is the larger one. And it makes no difference whether Cmin belongs to the hot or the cold fluid. Whichever is applicable, you will keep it here because your Qmax is determined by that quantity. So by looking at this expression of effectiveness for a parallel flow heat exchanger, we can immediately see that it is a function of these two non-dimensional quantities. So one is the simple capacity ratio rate, or the smaller capacity ratio this thing. So Cmin upon Cmax. This is the respective thermal inertia of the system. And the other one is UA divided by Cmin, which we will now call it as the number of transfer units. So what is going on to the next slide, we see that the effectiveness relationship of heat exchangers typically involve these dimensionless group. This group UA upon Cmin is called as the number of transfer units, or NTU. The second group, of course, is Cmin upon Cmax, which is just the ratio of the respective heat capacity rates of the two fluids. One is the minimum one and one is the maximum one. Either of the two, it can be this. The minimum can be cold or hot. It doesn't matter. So what do we see? That if U, which is overall heat transfer coefficient, which depends on the mass flow rate and the geometry of the heat exchanger, if this is given, for example, for a given material medium and the type of flows in a given heat exchanger, then U can be estimated, which we have seen in the earlier lectures. Cmin is also, we can estimate it. So for specified values of U and Cmin, what does the NTU tell you? The value of NTU is the measure of the surface area. You can see here AS. So larger the NTU, the larger the heat exchanger. So now you can immediately see that the NTU as a non-dimensional parameter is a function of effectiveness of the heat exchanger and vice versa. So the effectiveness of heat exchanger is a function of number of transfer units and the capacity ratio. So this is what is a very interesting and important outcome of this analysis, which started with the simple energy equation and trying to find out the mean temperature difference between the two fluids. So now for a parallel flow heat exchanger, we have just derived this. So it will come out to be epsilon, which is the effectiveness, is 1 minus exponent of minus NTU 1 plus small c, where small c is this capacity ratio. It is the second non-dimensional number which we were talking about. So these so we have just derived the first one, and for the others there are text available where you can see this derivation, and you will see that this effectiveness is a function of NTU, and this can also be this particular expression can also be let's say represented in a graphical format, which you can see here on the right hand side. In fact, all of these equations can be converted into a graphical format, which we will just see in the next slide, which is slide number 84. So what you see here is that for small NTU values, they all more or less are the same. They are identical. They don't differ too much when the NTU is very small. So that goes into the exponent here, and it is easy to understand why for small values of NTU this expression will not change much, and you will have more or less identical values irrespective of what is the value of small c, which is the Cmin and Cmax, the ratio of Cmin by Cmax. So you can see that it varies from 0 to 1, of course, this value, and depending on your heat exchanger you will get a particular value, and you can extrapolate if you have to get it from the graph. So if NTU is known and the ratio of the heat capacity rates is known, you can get the effectiveness of the heat exchanger. You can either use a graphical solution or you can use an analytical solution. So in the next slide you will see that all these graphical solutions are also shown to you, And here the subject of the formula is NTU. You can even make the subject of the formula as the effectiveness. So in the previous slide you saw the effectiveness was on the left hand side and it was a function of NTU and C. And the same expressions can be written with the making the NTU as the subject of the formula. So here the NTU is a function of epsilon and C. So depending on which quantity is the known quantity and which is the derived quantity, you can use the appropriate formula taking it from the data book for different types of heat exchangers. For example, double pipe parallel flow we just derived. Then you have counterflow heat exchanger. You have shell and tube, one pass or two passes. You can put that value here and get the value of effectiveness. Similarly, you can have cross flow heat exchangers with single pass, mixed or unmixed heat exchangers, and all heat exchangers where C is equal to 0. Please recall, you will remember that for boilers and condensers, you will have the small c as 0 because your C max becomes infinite. Because your thermal capacity rate of a phase change process, there is heat transfer taking place in the form of latent heat, but there is no temperature drop. So therefore your small c will become 0 for all heat exchangers which involve one of the fluids in phase change process, that is boiling or condensation. So these are the formulas or the analytical expressions, and this on the right hand side are the corresponding graphical solutions of the same equations. Some important points can be noted now from this relationship between the effectiveness and the NTU. So the first thing is that when all the inlet and outlet temperatures are specified, we will recall that the size of the heat exchanger can easily be determined using the LMTD method. So we are on slide number 85 right now. Alternatively, it can be determined from the effectiveness-NTU method by first evaluating the effectiveness from its definition and then the NTU from the NTU relationship, either graphical or analytical. So any problem can in fact be solved by both the methods. There is, it's not sacrosanct that you use one method or the other. However, you will appreciate the fact that when only two temperatures are known, which are the inlet temperatures of the hot fluid and the cold fluid, in that condition, the LMTD method will become iterative in nature because you do not really know the outlet temperature and you have to keep iterating till you get the specified outlet temperature. It will become tedious, and therefore since effectiveness can be independently determined even if the inlet temperatures are only known, and therefore we will use in those cases the NTU effectiveness method and try to do the sizing of the heat exchanger. So moving on to slide number 86. Now what we have done here is that we have created one particular composite figure by picking up the C equal to 1 cases for all the three types of heat exchanger, that is the counterflow heat exchanger, the cross flow heat exchanger and parallel flow heat exchanger. It's the same data or the same expression, just C has been taken to be equal to 1 for comparison. Because the C values can go from 0 to 1, and here we are comparing for a particular C value, which is the non-dimensional C min upon C max. So what do we note? That this particular expression, it increases rapidly with NTU, the effectiveness, which is on the y-axis here. The effectiveness increases rapidly with NTU for small values up to about 1.5. So you can see this is changing very rapidly from 0 to almost 50%, crossing 50%. Therefore, the use of heat exchanger with an NTU which is greater than 3 and thus a large size cannot be justified economically. So because, for example, you see parallel flow here, after NTU becomes about 2.5, even if you increase the area, nothing much is going to happen because whatever heat transfer was supposed to take place has already taken place, and now the remaining delta T's are so small between the two fluids that even if you make a very large heat exchanger, the delta T or the thermal potential or the voltage drop is in itself very small, and therefore not much is expected to happen. So therefore anything which is more than about 2, 2.5 or maximum 3, for example, there is no point in making a heat exchanger which has such a large surface area. So it is like a point of diminishing returns. You keep on increasing the area, your effectiveness increases, but after a while the slope changes drastically and doubling the area doesn't double the effectiveness, so to say. Okay, because it's a logarithmic variation of temperature which is happening. So thus a large size cannot be justified economically, since a large increase in NTU in this case corresponds to very small increase in the effectiveness. Again, another important thing, for a given NTU and capacity ratio, the counterflow heat exchanger has always the highest effectiveness. So therefore the counterflow heat exchanger, if you recall, the hot inlet is let us say from the left hand side, so the cold inlet becomes from the right hand side, and therefore you get a very good potential difference between the two fluids throughout the heat exchanger, and therefore it always gives you a better option. So if you have an option of counterflow, one should always use it as compared to parallel flow or cross flow heat exchangers. The lowest effectiveness values are encountered in parallel flow, which is also obvious. Of course, if the NTU is very small, and but then what happens is that when NTU is small, all of the three are behaving similarly. However, the effectiveness is also very low. So it is not justified actually to use an heat exchanger with such a low effectiveness. So these analytical expressions between effectiveness and NTU, they provide a lot of insight into the sizing problem. How big should be the heat exchanger? What is the effectiveness? Can we increase the effectiveness more than what it is happening right now? How much increase will happen if you increase the NTU of a heat exchanger, and things like that. So moving on, uh, the effectiveness of heat exchanger is independent of the capacity ratio for NTU values less than 0.3. We have already noted that. And for a given NTU, the effectiveness becomes maximum for C is equal to 0. So that is also interesting. For any particular heat exchanger, when C becomes equal to 0, you will notice any of the analytical expressions which you choose, that your effectiveness becomes more. So if you have a boiler or a condenser, for example, then because of the phase change process, and the fact that there is no delta T happening throughout the heat exchanger, the same temperature of either boiling or condensation prevails, and therefore there is no change in the potential difference as far as one fluid is concerned, and therefore it is logical that when C is equal to 0 for a given NTU, the effectiveness becomes maximum. And of course, when the heat capacity rates of the two fluids are equal, then you will get a minimum that also can be ascertained from the analytical expressions and the graphical figures which are given alongside. Now comes the question of how to select. You have seen there are several different types of heat exchangers which are in the market. It is not straightforward to pick up just one and use it. So how do you select? So there are broad guidelines. One is, the first important thing to note is that there is a lot of uncertainty in the predicted values of U, and you have seen that how fouling affects the heat exchanger overall heat transfer coefficient, and therefore you should not take these U values as sacrosanct once you do some hand calculation. Most of the times the U values may come out to be lower than what you are estimating because of fouling and other reasons. Then there are variations in the mass flow rate which also occur over a period of time because of choking, because of maldistribution and things like that. So it is natural to tend to over design heat exchangers. So unless there is a very let's say stringent maintenance schedule which tries to remove all these fouling in a periodic fashion and tries to renew the heat exchanger again back to the design basis calculation, usually it is the industry tries to give some factor of safety and tries to over design a heat exchanger. Any increase, you will recall from our original discussions on transport phenomena, that any increase in the heat transfer is usually accompanied by an increase in the friction factor and therefore the pressure drop also. So the heat transfer enhancement is usually accompanied by increased pressure drop and therefore pumping power increases, and therefore one has to be always careful about trying to enhance the heat transfer monotonically and not trying to and not paying attention to the pumping power, This is not done. Both has to be seen simultaneously because there is a cost of running the heat exchanger, which involves not only maintenance but also the pumping power, which is a primary requirement for convective internal flows. So one has to keep an eye on that. So any gain from the enhancement of heat transfer should be weighed against the cost of accompanying pressure drop. This is logical. And also, if out of the two fluids, for example, if you have one of the fluid which is more viscous, since we know that enhanced viscosity will give you enhanced pressure drop, and therefore we would like to put such a fluid into the heat exchanger where the area available is more, which is usually the shell side. So therefore the shell side pressure drop is usually lower than the tube side pressure drop for the same mass flow rates, because the available area in the shell side is much larger. And therefore it is a common practice to put the more viscous fluid on the shell side and the fluid with higher pressure for the tube side, because the tubes can withstand higher pressure, internal pressure, because of your hoop stresses and the longitudinal stresses, which are becoming better and better as you decrease the diameter of the tube. And therefore anything which is moving with a higher pressure must flow in a more stronger element of the heat exchanger, which happens to be the tube rather than the shell. Then also you have to understand that the heat transfer, the selection of a heat exchanger also depends on many factors, which are the heat transfer rate, the cost, the pumping power, the size, and the weight of the heat exchanger. Where is it going to be kept, for example, whether it adds on to the payload capacity, for example, in a submarine or in a ship. How big is the heat exchanger, what is the weight will also be of importance. If it is a compact heat exchanger, if it is a compact system which is being designed, then again the weight and size comes into picture. The type will also depend on what type of fluids you want to use and what is the type of condenser available, or what type of ambient material is available. Is it air cooled or is it water cooled, for example, or are you cooling some oil whose Prandtl number is high, for example, and things like that. And then of course there is material compatibility has to be seen between the construction material of the heat exchanger with the fluid which is flowing inside it, and what is its long-term fouling behavior, and whether corrosion in the environment in which it is working, whether corrosion is an important parameter, and things like that. The rate of heat transfer in the prospective heat exchanger is of course given by mCp delta T. And then with this considerations, you also have to see the annual cost of electricity associated with the operation of the pumps and the fans which are used for pushing the fluid inside the heat exchanger. So typically, for example, operating cost may come out to be pumping power in kilowatts multiplied by how many hours the heat exchanger is running. That means the pumps are running, and multiplied by the unit cost of electricity in rupees per kilowatt hour, and this will give you the operating cost. So you have to find out the long-term operating cost, you have to find out the long-term maintenance cost, you have to also see whether there is enough space available for maintenance where the heat exchanger will be installed, because you have to take out the end channels, you have to remove the shell tube side sometimes, you have to clean the tubes, you have to put some equipment there. Also you have to check the vibration levels and the foundation, possibility of erecting a foundation at the local level. Also regular maintenance has to be done for the heat exchanger, so personnel has to move inside for not only doing the maintenance but taking regular data, so that the effectiveness and the efficiencies can be calculated. So all these parameters are there which will determine how do you select a heat exchanger. So finally, concluding this lecture at slide number 90, we have seen the way in which effectiveness-NTU method is applied to heat exchanger analysis. We have also seen some salient features of heat exchanger effectiveness and its relationship with NTU were also noted. How do they behave? We have seen the analytical expressions. Of course, you are not expected to remember these. You can derive for simple configurations, you can derive. But for complex configurations, you need a data book which will be supplied or whenever you solve a problem or you are designing something, you should refer to a proper design handbook to get these effectiveness NTU expressions. And lastly, we have noted that the selection of or design of a heat exchanger depends on several factors which need to be considered before making the final selection for a given purpose and for a given type of heat exchanger. So with this, we conclude this entire chapter, which is chapter 13, on heat exchanger design and analysis, and we are on slide number 90 right now.